All right, well, welcome everybody. My name is Eric Calderup, and I am a member of the BIPSA USA Education Committee. And before I introduce today's webinar, Ajit, can you advance the slide, please? I would like to welcome the BIPSA USA members who are in attendance and thank you for your support. And also, if you're not yet a member, please consider joining so you can find info at the ibpsa.us website. And next slide, please. So also check out these upcoming events. Just on Friday, there's going to be a kickoff meeting for a new working group. This is the Education Committee's QA/QC working group. So if that's a topic that interests you, check that out. You can find, again, info on the bipsa.us website. And then on the 18th, the Wisconsin chapter has a webinar on small businesses in the energy modeling and simulation marketplace. And then finally, upcoming in September, we return to a live in-person conference, the 2022 joint conference between ASHRAE and the BIPSA USA, Building Performance Analysis Conference and SimBuild. So definitely check that out. Okay, next slide, please. So quick announcements, please be aware that this webinar is being recorded. And then we're going to plan to have time for questions at the end. Please use the Q&A feature of Zoom. If you type your questions in chat, we may or may not see them. And then if you do want a PDF of the slide, those will be available next day or so. We'll send out an email about that. All right, so my pleasure to introduce today's presenter, Ajit Naik. He is a vice president of Bauman Consulting. And he received his mechanical engineering education at University of Michigan and then at the University of Wisconsin-Madison. And his 10-year energy engineering career has taken him around the world from Wisconsin to Germany and then back to Illinois, where he's now based in Chicago, where he also serves as a leader of BIPSA USA's Chicago chapter. Really happy to have him here today. And his topic today is an introduction to predictive energy modeling. So welcome, Ajit.
Thank you, Eric. I really appreciate the intro. Also, thank you everybody for joining us today. As Eric so kindly introduced, today's subject is an introduction to predictive energy modeling. So today really is about a high-level look at what predictive energy modeling is, understanding how it differs from the compliance building energy modeling that's a little bit more commonly known, understand the motivation for applying the predictive modeling process, both to new and existing buildings, understand how to deal with uncertainty during the predictive modeling process, and also to identify industry references important during the predictive modeling process. So again, this is really designed as a primer and an introduction for people who aren't very familiar with the process. So just to start out, had a question for the audience here, which should pop up in a moment. What's your experience with building energy modeling? So Eric, if you could go ahead and launch that poll. Let's give everybody 30 seconds to fill that out. So again, looking to understand your experience with building energy modeling. Starting to come in, Eric? Okay, all right, so it looks like we're across the board here. We have mostly people without a lot of experience, students and beginning practitioners, and then about half also expert practitioners. So great, hope to share something of value to those of you who are just starting out, and also hope to get some interesting viewpoints and comments and considerations from those of you with more experience. So I thought I would start out for those who are just starting out here with what is energy modeling. Energy modeling, for those who don't know, is the virtual or computerized simulation of a building or a complex of buildings that focuses on its energy consumption, utility bills, life cycle costs. It's a computer model that takes different types of inputs, things like weather, enclosure, thermal insulation, windows, foundations, details about the occupants, the number, their activity levels, how often they're there, information about appliances, their power draw, how often they're used, lighting, HVAC systems, domestic hot water, and even utility rates. So everything that in real life affects your energy bills and your energy consumption is also considered as an input in an energy model. It gives us useful outputs, including energy usage broken down by fuel type and end use, peak loads for each of these end uses, as we discussed, things like heating, cooling, lighting, fans, pumps, water heating, and utility costs. This can be just fixed costs. It can include things like time of day tariffs. So really, anything that would affect a building in real life can also be created in an energy model. Before we get any further, one critical thing for energy models, regardless of what type they are or what they've been done for, is a robust quality control process. Garbage in, garbage out, as they say. So it's very critical at all phases of the development of an energy model through the input and output process to implement a quality control process. So energy modeling really comes in a couple of flavors. One of the main flavors is compliance modeling. So what is compliance modeling exactly? So it's one of the reasons compliance modeling is done to demonstrate compliance with some requirement. For example, energy codes. So at the top row, we see things like the IECC, ASHRAE 90.1, California's Title 24, the International Green Construction Code. Codes often require energy models to demonstrate that a building will meet a certain energy code requirement. Third-party certifications, familiar ones like LEED, but also Green Globes, Enterprise Green Communities, Energy Star, among many, many others, all require compliance modeling. All of these standards really boil down mostly to 90.1, which is the underlying backbone behind all of these, but which provides two sets of rules for compliance modeling. One of them is Section 11, the energy cost budget, and the other is Appendix G, the performance rating method. Without getting too much into detail about these, both of these methods allow modelers to use standard default assumptions for instead of identifying real world values for many things like air tightness, usage profiles, internal loads, weather data. It's very common to use TMY data, 20-year averages, when running compliance models. So this means while an energy model can be used to demonstrate compliance with a certification or a code, it often means that these outputs frequently diverge quite widely from real world performance down the road. So they are often very useful in predicting how much energy a building will actually use. It's for several reasons. So compliance modeling at its core basically requires two models, one for the proposed design, and then another imaginary building that has the same shape, program, and operating parameters as your proposed design, but that has all code minimum envelope and MEP systems and no exterior shading. You can kind of see that on the image on the left too, where a proposed design energy model is compared with its baseline energy model. So after completing these two energy models, if the energy model for the proposed design shows a better performance than this imaginary baseline, sometimes there's a minimum threshold, sometimes it just has to beat it, then the building design is in compliance, thereby compliance modeling. Performance is usually assessed in terms of energy cost, or sometimes a cost-related indicator called the performance cost index. But again, it doesn't really matter whether the energy model's performance matches the real building at the end of the day if the intent of the energy model is just used for compliance. It only really matters if the proposed design beats that imaginary baseline building. That brings us as a comparison to predictive modeling. So predictive modeling, as you might expect, stands in opposition to simple compliance modeling by having several key characteristics. A predictive energy model is an energy modeling process that's used to reliably predict real-world building energy usage. It's not just used to compare a building against an imaginary baseline. It uses simulation inputs that accurately reflect all real-world aspects of a building, not just standard reference values. It is a model that reduces and or quantifies uncertainty in assumed simulation input using different analytical techniques that may be different for different applications. And it's one that can be used to accurately assess the potential impact of energy conservation measures under consideration. And specifically, these can be later successfully validated by monitoring after implementing ECMs. So the real critical thing that differentiates predictive energy modeling from compliance energy modeling is a focus on quantifying uncertainty and a focus on validating the results by measurement and verification after the modeling process and implementation has been completed. To summarize, compliance modeling really just compares a proposed building against an imaginary baseline, whereas a predictive energy model is just one model and its purpose is to accurately predict performance as much as possible. Compliance modeling has a relatively low input fidelity. It allows using standard reference values for weather data, internal loads, and usage profiles, whereas predictive energy modeling requires real-world values or analytical techniques directed towards addressing the uncertainty in these if unknown. The outcome of a compliance modeling process is considered successful if the proposed model simply beats the baseline, regardless of how it compares to real-world building energy usage, whereas predictive energy modeling is only considered successful if the actual performance after implementation can be measured and verified to match the energy model's predictions within an acceptable tolerance.
Say, Ajit, can I just interrupt quickly with a question here?
Please.
Jayati was asking about the imaginary baseline building and what is it based on in the compliance energy modeling process?
So that's a great question. So going back, there's actually two different strategies here, and the baselines kind of differ a little bit in each one. The basic purpose behind the Section 11 baseline was to represent kind of a code minimum version of the design that you're proposing. So the baseline in that case kind of looks similar. It has similar HVAC systems and everything, but it's a code minimum efficiency versions of these. Appendix G is the baseline more typically represents common practice. So if you're building a school and it has all sorts of advanced systems, the baseline might look more like what typical systems are for a school in your climate zone and location. But either way, the baseline doesn't represent an actual building. It represents a fictionalized, more average or standard version of yours. Hope that answers the question. Okay. Real high level here, I want to talk about the predictive energy modeling process steps. There are several resources, most importantly, ASHRAE Standard 209, which covers the energy modeling process in extreme detail from phase by phase, step by step, who to do, what to look at. So this isn't about that. This is really just a high level look at kind of what defines the predictive energy modeling process. The first and foremost is to work with stakeholders to establish measurable project performance goals. So the key word here is measurable. These goals have to be something that you can look at, that you can count, and that you can validate after the fact. We collect building data. This looks similar to the compliance modeling process, except it's more rigorous. We need to accurately understand what the building is going to be doing. This could look different for new and existing buildings, everything from project documentation, stakeholder interviews, site visits, participating in team meetings, really anything. But all of this has to be validated. Developing the energy model, that process is described elsewhere in great detail, so we won't get into it here. But again, it has to be looked at a sufficient granularity, looking at the energy usage at several different levels of breakdown, and also to implement a quality control process throughout the entire modeling process. What really differentiates the process is addressing model uncertainty. So we've discussed several times that it's really critical that the inputs have a high level of fidelity, that they accurately reflect real world. In existing buildings, we have, while all these inputs aren't known, with existing buildings, the strategy for bringing this about is calibrating the energy model. So if we assume inputs and we run our model and we come out with a result that's different than what's actually been measured, than our historical utility bills, than our BMS trend data, then we know something isn't right. And we work to refine our model inputs until our model is calibrated, when it can then be used for further analysis. For new building projects where we don't know this, where there isn't a right answer, we handle uncertainty by performing sensitivity analyses on unknown variables to quantify uncertainty. So if you don't know what it is, test different versions of what it could be, test different possibilities to understand its impact on your design and its performance. Next, it's our due diligence to facilitate decision-making. Always have a clear understanding of the goals. Use the energy model to identify and test different strategies. Work closely with other project stakeholders to obtain costs and understand feasibility. And then finally, advise project teams only on cost-effective, comprehensive strategies to hit their goals. It isn't important to say you could do this or you could do that, or talk about a bunch of things that aren't really relevant. It's always important to tie your analysis back to your understanding of the goals. And finally, it's the modeler's responsibility to assist with validation. What that doesn't mean you need to perform the validation yourself, but you have to set the project up for success. That involves clearly documenting energy model inputs and outputs for future transparency, and also working with the project team to incorporate sufficient monitoring requirements into your design. Making sure that if your model has a certain level of detail, that the equipment installed in the field can also collect data at a sufficient granularity to validate your model at the input that you put in. How do I select the right tool for performance modeling? This is another question that's out there. So IBIPSA USA does maintain the best directory, a directory of the building energy software tools. There are dozens and dozens and dozens and dozens of packages out there. Many of you may be familiar with some of the packages that I have listed on the screen, but there are many more than these available. There are really a few critical points that you want to keep in mind when selecting a software package. Number one, it should be able to model your building and your building systems, as well as the strategies that you're proposing. Not all of these software packages can model every type of building or every type of building system equally or evenly. So having an understanding with the capability of your software is essential before picking a tool from your toolkit. Similarly, it's important that you have the required level of expertise to use and to interpret your software output. Sometimes it may be better to use something that you know better when it's really critical to get a high level of fidelity in your inputs and outputs. Having the right level of complexity, this involves that planning for verification. Some energy modeling software gives outputs only on an hourly basis. Some of them you get only on a monthly basis. Some of them you can define your time step and have outputs given at whatever level you want, down to minute levels or even sub-minute levels. Really understanding what you're going to be able to verify is critical here. If you're working in an existing building that has only old equipment and monthly utility bills, it's questionable how valuable an hourly energy model is going to be when you cannot validate at that level. If you're working with a high performance data center with an advanced energy management system that's looking to improve its operations, you're not going to be doing your due diligence if you don't use an energy modeling tool with sufficient capabilities to model the systems at a small enough time step. I'm going to stop here. Now that we've kind of covered these two types of projects, and ask the audience, what kind of energy models have you guys worked on? Have you guys worked on compliance models primarily, predictive models primarily? Be surprised to hear that, but could be. Both or neither. So give everybody another 10, 15.
See the answers coming in. While we're waiting, Adrian had a relevant question about, what is the ratio of compliance modeling projects to predictive modeling projects? Like, which is more widely used, and what do you foresee will be more predominant in the future?
Oh, that's great. I actually talk about this in the next section, so I'll come back to that. But right now, I can't speak to everybody, but historically, I think that lead and code have really driven the market, and compliance modeling has really dominated. But there are some interesting changes that are happening, both regulatory and elsewhere in the market, that might change things, which we'll get to in a second. But actually pretty good. Looks like most people here have worked on both types. Again, about 50% of the folks here have worked on both types. The second group is 30% of people have worked only on compliance models. So I guess, Adrian, this kind of gives you your answer here. It looks like most people have worked on either just compliance models or both, but a minority of people have worked on only predictive models or just that. So thank you, Eric.
So are you open to one more question about predictive modeling?
Always.
This was in the chat from Yuan. Is the model form uncertainty addressed in the predictive energy modeling framework process? How do you deal with the uncertainty within the software tools themselves, not just the inputs.
That's great. So just quantifying it and understanding it and including it in the goal setting process. There is always in any modeling or calibration exercise a certain level of uncertainty, not only in the modeling, but there's also uncertainty in the measurement, right? When we install sensors in the field and collect the data via BMS or what have you, there's also error introduced in those portions of it as well. So quantifying the sources of uncertainty, establishing how you account for uncertainty during the validation process, and making sure that you are accurate to a tolerance level within that uncertainty is how that would work. So switching gears a little bit, I want to talk about why predictive modeling. What are some of the motivations for predictive modeling? So we talked about in some detail already the motivations behind compliance modeling, right? And those are mostly A, you needed to get a building permit, you do not pass go, can't proceed without it. Or B, you wanted to get your LEED certification or your Energy Star certification for funding. Predictive modeling is used for a variety of reasons, but I want to talk about a couple of them that I find the most interesting. Really, it's wherever somebody cares about their actual performance and has a specific measurable target. Easy ones to start out with, top row, is other third-party certifications that have zero energy requirements. FIAS, Passive House Institute, the Living Building Challenge, IFLI's zero energy certification. All of these certifications require, they don't have any ASHRAE requirements. You don't need to do a 90.1 model, low baseline model. Your building just needs to not use more energy than it produces on site. And so that's a pretty clear target, a target of net zero. So that's a call for a predictive energy model. There are grant programs that help projects, mostly public sector projects, hit net zero goals. For example, the Illinois Clean Energy Foundation, NYSERDA in New York, the Energy Trust of Oregon, they all have grant funding programs to help projects hit net zero. But that final bit of the grant, once awarded, that final disbursement doesn't hit until you validated through a year of performance that your building actually performed. So if you're counting on this grant money to make your building financially solvent, you have a serious motivator to make sure that your building actually performs as predictive. Again, a call for predictive energy modeling, not compliance energy modeling. Lastly, and what I personally find the most interesting is building performance standards. So several municipalities around the country, I should say a handful now, but there are several that are in the work, and this is gonna keep growing, are building performance standards. So Washington, D.C. has one, Washington State just rolled one out, the city of St. Louis has one, New York City has one as well. What these are buildings are basically required to report their building performance every year, and they're compared to their peers, and there are ramifications for either meeting the average performance, meeting this performance standard, or failing to meet them. So while the first two are really more about new construction, kind of marquee buildings, new buildings that are trying to really change the market from that aspect, these municipal building performance standards affects everyday type of buildings and put performance requirements on them where there were none before. So all of these require buildings, whether new or existing, to hit specific measurable targets that must be validated after the fact, making all of these great motivators for the predictive modeling process. I want to talk about a couple of case studies now, just to kind of give an example of kind of what the predictive modeling process looks like. And I want to talk about two pretty different case studies, just to kind of show how this way of thinking can be applied to projects, whether they're low budget, small projects with small clients, or big budget, high projects with marquee clients. So let's start with the former first and talk about an existing building. So I want to take you all to our nation's capital, Washington, D.C., where the Department of Energy and Environment has established the Building Energy Performance Standard. So again, like I discussed, this is a This is a standard that requires buildings to benchmark. That's been required since 2013. They report their energy usage, their utility bills to the portfolio manager. Then the DC basically compares your building's performance to other buildings' performance and assigns you a score. And the new standard says that, which just went into effect last year, says you need to be better than the DC median in order to be in compliance. So there's basically 6-year compliance cycles. The first one started in 2021. If a building isn't better than the median at the start of 2021, it has until 2027 to bring it up there. It either has to bring it up to the median, or there's some other ways of achieving it, like EY reductions or prescriptive measures. And then at the end of the cycle, if it's not in compliance, there's a fee levied, right? And then the cycle starts again, but the target is now lower, since all of the buildings have implemented efficiency measures and everything to bring it into compliance. This system is designed to march down the energy usage of the district over time. Right now, it's only buildings greater than 50,000 square foot covered. Next cycle, starting in 2027, so all buildings over 25,000 square foot. The third cycle, starting in 2023, so all buildings over 10,000 square foot. So this really is coming to a building near you soon. And so, you know, like I said, there are different ways for projects to come into compliance if they're not. They can meet the median, they can do some improvements, but it may be in their best interest to actually hit the median every time, because, you know, this target is going to progressively increase each cycle. And just to talk about what the fines are here, these fines are extremely steep in Washington, D.C. So like they range from $500,000 up to $7.5 million for large buildings. So really, you're talking about small buildings owners can have to pay hundreds of thousands of dollars for this. So this is not chump change. This is really designed to drive the market. So all people who own buildings in Washington, D.C. have a strong interest in making sure their buildings comply with the standard by 2027. Otherwise, they could face steep fines. So I'm going to talk about a case study about an office building in DC, but just out of curiosity, I wonder here, no cheating, people, please, if folks can guess what the median Energy Star score is in Washington, DC. For those who don't know, the Energy Star score compares your building to the national median, which is 50. So buildings better than 50 mean they're doing better than the median, and buildings with a score lower than 50 mean they're doing worse than the median. That's nationwide. I'm asking here what the median score for an office building is in Washington, D.C. What do we see, Eric?
We got about 2/3 of you answering. Got a few more answers trickling in. Another 10 seconds, folks. All right.
All right. Okay. So we got 71 at number 1, 51 at number 2. So great guess. Most of you guessed right on point. The average Energy Star score of an office building in DC is 71. So that means the average building in DC is better than 71% of the rest of the country. So that's the score to beat. So if you don't have an Energy Star score of 71 right at the start of it, you're already not in compliance and have to bring your building into compliance by the end of cycle 1 in 2027. So the building we were working with is an office building in Northwest DC. I can't share the name, but it's about 62,000 square foot, 37% window to wall ratio, all electric building, built in 1968. There were some recent upgrades, partial window upgrade, partial lighting upgrade, partial FCE replacement, some new baseboards. There's a VAV air handling unit, but there's still very ancient chillers, very ancient pumps, vintage 1968, rehabbed a couple of times since. Looking at the scorecard as of 2019, which is the benchmarking data that was used to evaluate compliance at the start of the cycle, this project had a score of 66, right? So this isn't too far off, trying to get to a score of 71. We see a few metrics here showing kind of the source EUI and site EUI improvements that they needed to target. Totally, they needed to reduce their site energy about 7% to hit their goals. Per our calculation, the initial fee is about $210,000 for this. So with all actually originally established at 620,000, but there are methods to further reduce or avoid this fee and lower it down to 210 as via pre-adjustment process. So really, this building owner has the choice, either pay a fine of $200,000+ in 5 years' time, or invest intelligently in their building in a way that would meet the goals. So first step, as we discussed, was to understand the target, right? So we actually ended up looking at a 13% EUI site reduction by 2026, not just 7%. Again, this is to account for uncertainty, to position the building for the next cycle. So we did that in our goal setting. We built the energy model based on building info. We went on site, interviewed stakeholders, reviewed documents, looked through the 2019 utility bills. We next built the model. We calibrated it to within 10%, ideally 5%. And then we calibrated the model to test potential ECM's impacts on the utility cost reduction. We also obtained implementation costs, and then we were able to recommend only cost-effective ETMs that made sense for the building. For this project, we used RedScreen Expert. This is a monthly energy modeling software developed by the government of Canada. It's not a first principles model. It's like an engineering reference model. It only works monthly. We can't get results out at a higher fidelity than that, but this is an old building with no trend data available, only monthly utility bills available. So this was an appropriate tool out of our toolkit for this project. With our goal, we were able to identify several ECMs, categorize them as go, no go, and maybe, not just based on cost and impact, but based on how they would have other synergies, help them meet their performance requirements, defer operation and maintenance costs, and ultimately recommend things that were only relevant to them. We were able to sort these into ECMs identified between those which were low cost and no cost, that had very fast payback periods, relatively immediate, that were no-brainers to recommend, versus capital intensive energy efficiency measures. So these measures, may have longer payback periods, more high levels of investment, but may also be useful for the building in other reasons. Just looking at these costs here, $200,000, $300,000, $400,000. So there are consequences, to not getting this right, to not calibrating your model, to not setting your goals properly. It could be the difference between investing $300,000 and still not meeting your goal and being subject to a $210,000 fine. So having this level of confidence, quantifying your uncertainty, handling it with the calibration process, and accounting for it in your goal setting was really critical for us here. Want to switch gears again for a minute here and then talk about what this might look like in a new building. So for old buildings, it's very clear, we have historical energy usage, we calibrate our energy model, we know what the building looks like, there's users we can talk to, we can go into the building. There's a lot of things that are really working for us here in terms of information and what we can do with it. However, with new buildings, we really don't have a lot of that. The building doesn't exist. The shape of the building doesn't exist. We don't know what it's going to be designed as. We don't know how it's going to be used. We really have no idea. So there's a lot more unknowns, and we have to deal with this uncertainty in a different way. So to talk about this, I want to talk about another case study, the Brock Environmental Center building. This is in Virginia Beach, Virginia. It's built in 2014. So this is a Living Building Challenge certified building, net zero energy certified building. It's been operating net zero since it opened up 6 years ago. A lot of high performance systems in here, and it's a pretty interesting building. So again, the predictive energy modeling process, though, for this high-end new construction Living Building Challenge building isn't really that different from the predictive modeling process for a 1968 office building facing municipal fines. It's to understand the target. Here it's pretty easy. The target is net zero. We build an energy model, again, based on building info collected via design document review, stakeholder meetings, design meeting participation, Again, being more involved with the teams here is really critical. There's no historic data available, so we must make assumptions, right? So the way to handle these unknowns is via a sensitivity analysis on unknown model inputs. So things like daily operating hours, seasonal operation, partial occupancy levels, different required lighting levels than what's designed, people having different comfort requirements and setting the thermostat at different levels, having hotter or colder average weather, user error, people forgetting to turn things off or leaving the windows open. When we went through this process here, and in general on any new construction predictive modeling process, it's important to test different scenarios for these uncertain variables. You should test a wide range of future operating scenarios, and we should also test the most likely future operating scenarios. And when making design decisions, especially those that impact first costs, we should take these uncertainty sensitivity analyses into account. And that's what we did at this project here. The software choice used for this project was Energy Plus. So Energy Plus is capable of extremely detailed analysis. It's capable of modeling the geothermal systems that were proposed for this project. It was capable of doing things at an hourly and sub-hourly basis, which was also included in the measurement and verification specifications for the project. So for this higher end project, a higher end tool was required and used. This wasn't the only tool used for this project. We also ended up using IES to run a natural ventilation study, but for the energy heavy lifting was primarily done in Energy Plus. So once the model was built, sensitivity explored, we thought about how to express these design decisions to the client here. Really critically, this project was looking to have net zero operation, right? That means to say no more energy use on site than it produces. So with a pretty specific target, it's easy to test different strategies to see how they achieve the goal. So being in Virginia, a pretty warm place, we were talking about more insulation, our 35 walls, our 30 floors, our 50 roofs. This isn't commonly done in Virginia. However, we got some savings out of it, 27,000 kBTUs per year. It cost $22,000, which was, a pretty big buck it's a small building, 10,000 square feet. Client didn't love it, but we looked at how many PVs it would take to generate that same amount of energy. And it was 11.2 kilowatts, and that cost $44,800. So it was actually twice as cost effective to add more insulation than PV. So rather than looking at it by saying that, insulation costs $20,000+ and only gets us 27,000 kBTUs per year, it was, again, always bringing it back to the goal. Our goal is net zero. And what are our options to get towards this goal? It was more cost effective to use the insulation, and that's what the building has. It was a similar story when looking at the glazing for the building. So again, the energy savings here is 19,000 kBTUs per year, right? So this is like $750 a year. It's not like a huge dent in the operating budget, but when you look at it from a first cost perspective, again, it takes 25 PV panels to generate that same 19,000 kBTUs per year, 8 kilowatts of PV, and that costs $32,000, right? So having even though it might not seem like it makes much sense right away, or it might have like a 30+ year payback to invest in triple pane glazing, when you look at it from a trade-off basis, right? I have to hit net zero, and either I'm going to invest in this PV panels, or I'm going to invest in this triple pane glass. It starts to make a lot of sense when you communicate, your design decisions with this specific goal in mind. So the glazing had a 36-year payback. The PV had a 44-year payback. When you look at it like that, none of them look attractive. But when you compare it to the goal that you need to achieve, the glazing clearly became the more attractive choice. Again, so we were able to, through an optimization process like this, reduce the site energy about 30%. And once the design was baked, we looked at it some more, identified opportunities to really shave this energy down, looking at task lighting, looking at right sizing the pumps to operate them on a more favorable point of their efficiency curve, implementing smart plug load controls, implementing natural ventilation strategies. Through this, we were able to drive down the energy usage to an optimized EUI of 16.5. The roof was able to handle that plus some more. We ran sensitivity analyses on this completed analysis and were able to identify that even with our worst case sensitivity scenarios, the roof mounted PV was sufficient to cover the site energy usage. So this building has actually achieved net zero energy usage without any offsite or like PV racks in a parking lot or anything like that. So the process is pretty similar, establishing goals, addressing the uncertainty, phrasing design decisions in a way that's centered around the goals. Regardless of whether you're working with new or existing building projects, there are several resources that I find enormously useful when working in this predictive modeling process. First is ASHRAE 209, great standard for how to incorporate energy modeling into the building design process, construction process. So regardless of where you're at, if you're kind of wondering, what do I do? What do I look at? How should I be doing it? This is a great place to start. ASHRAE Guideline 14, the measurement of energy demand and water savings. Great for validation when you're trying to give advice of how do I help these project teams, validate my model. Great place to look. ASHRAE Standard 211 for performing commercial building energy audits. Level 3 ASHRAE energy audit requires energy modeling. Lots of great information in there as well. Other things that aren't directly pertaining to energy modeling, like ASHRAE Handbook of Fundamentals, ASHRAE Standard 189 are great. There are third-party things like the AIA Guide to Integrating Energy Modeling into the Design Process, Rocky Mountains Institute, Building Energy Modeling for Owners and Managers, gives great advice on how to talk to clients. The Building Innovation Hub's Predictive Energy Modeling Primer. And lastly, but not least, is forums, Unmet Hours, energymodels.com. Asking people who have done this before is really invaluable when conducting any predictive energy modeling process or energy modeling in general. So, want to bring that to a few conclusions today. Is the predictive energy modeling process really accurately predicts a building energy performance? It sounds obvious, but most energy models do not. And predictive energy models must. It differs from compliance modeling, specifically by requiring that it requires them to predict real world performance. It's required for whenever there's a specific measurable target, what we discussed today, building performance standards or zero energy certifications. They always require you to address uncertainty, either via calibration or via sensitivity analysis. And they always must be validated. And they can be used to accurately assess the performance impact of potential measures. So that's really a primer for what it is, how it differs, and how to use it. So I'll pause there and see if there's any questions before we end today.
Yeah, we do have, we've got a few questions about the second case study, the new construction project. One of them from Patrick was, did you start in the conceptual phase?
Yes.
Using results to inform the design.
Yes, absolutely. That project would have never hit the performance it did if energy modeling were not incorporated from the earliest phases of conceptual design.
Yeah, so that's an important point. And there was also a question about, did you hit the mark on predicting energy consumption for that building? So did the predicted consumption, how did it compare to the actual consumption?
Yeah, it's operated. It has not operated one single year non-net zero. So it's demonstrably net zero since beginning operation.
Yeah, and I guess one of the follow-ons there was it possible to do end-use comparisons between actual and model? Was there sub-metering, for example?
There is sub-metering. Not everything is sub-metered, but the lighting is separately sub-metered, as are the mechanical systems. So while we can't necessarily separate, fans and pumps everywhere, but the HVAC system is separately modeled. So yes, there is a large degree of sub-metering there.
And I guess then, Tim, a follow-on was, has it been very net positive when predicted to be only barely net positive? I guess sort of, do you know how close to
I'll be honest,
prediction?
I have not followed up in the last year or two, but they do publish all of this information live. So if you want to take down my email address and shoot me an email after this, I will send you the dashboard to it. And if we've come out extremely net positive, we'll publish an apology.
Okay. There was a question about in this project too, and I guess more generally, insulating the envelope is more efficient than PV. Or more cost effective, I guess, or cheaper. This is a very interesting conclusion. So maybe a comment, but also just an example of some of the insights you can gain through this kind of analysis.
And I mean, it's really not cheaper. I mean, it only was cheaper if you're trying to hit net zero and you have a decision between PV and insulation and you're trying to get to zero. In lots of other situations, that might not be the case.
And probably, the cost of PV was higher when this building was designed. So
correct. And it was in Virginia, local incentives, market factors, this analysis would certainly look different today.
Let's see. Well, there was a specific question about the modeling tools, about modeling geothermal systems and whether IES could do that. You mentioned that Energy Plus modeled geothermal loops.
Yes, IES can do that. And for those not familiar, I think Matt Duffy a few months ago gave a pretty excellent webinar showing exactly how to run geothermal systems in IES. So if you're looking for guidance on how to do it there, he's the right person to talk to.
Right. And so Jat, you had a question. So will it be possible to mention one or two examples on when hourly results are important and when annual results are in a project? I guess, do you, I'm not sure I get that exactly.
I can at least describe it when we use it. So, right. So like RedScreen, like I mentioned, is a monthly energy modeling software. We use this really commonly when we get existing building projects that are older that have only monthly data, right? They just have utility bills. There's no BMS. Nobody's going to put in a BMS. That's not really on the table. So we use a monthly energy modeling tool because there really is no value to adding the higher level of fidelity because we're not going to be able to validate it. With most new construction projects, if you are working in the design phase, you can work with the mechanical engineer to indicate, what points in a BMS would be trended. And if I'm going to be able to get, hourly or 15-minute trend data from an air handling unit fan VFD, from a chiller compressor, from anything like that, then it's worthwhile using an hourly energy modeling software because I'll be able to validate my performance with ultimately measured trend data from the field.
Okay. Yeah. So Jati, if you had another question, please go ahead and expand on that. So Jorge had a question about natural ventilation. I think, natural ventilation, well, I guess, how do you address natural ventilation, both for the sake of energy savings and for potentially indoor air quality improvement processes and addressing
so for the project, sorry I don't have a slide on it here, but there we used IES and we used kind of like a bulk airflow. There's a flow simulation module in IES, which we use to basically validate the airflow throughout the building. And ultimately there, its quantity is whenever the temperature is below a certain point, the airflow will increase. And we integrated these two models. So the natural ventilation model, we exported the hourly airflow, through each zone, and we imported that into the energy model and, took credit for a positive cooling load whenever that system was in operation. So that's how that worked there. Implementation wise, how we implemented it at that project was very simple. There was a temperature sensor outside, inside, and whenever the conditions were favorable for natural ventilation, there was a big green light that would just light up and let everybody know that they can open their windows. And when the conditions were not favorable, that light would be red and people would know not to open their windows or to close their windows. So it works quite well, actually.
Yeah, and so there's kind of two related questions also, one in Q&A and one in chat. One is, are there ways to reduce the gap between energy consumption coming out of the compliance models and the actual measured energy consumption? So can we make compliance models more predictive, I guess, maybe is a question.
Absolutely. And I mean, it's kind of an artificial distinction, right? Like if you go look at ASHRAE standard 209, there's not like a chapter on compliance models and a chapter on, predictive models. It describes like the predictive modeling process. However, for one reason or the other, it's often due to constraints in the project. There's not budget to do it. People aren't motivated that way. There isn't really a clear goal on that set. It really shows the importance of things like building performance standards or net zero certifications or something that really requires you to set a measurable goal. Because, for lead or for code, where there isn't that requirement, there really is no motivation, right? People are motivated by what do we need to get this performance relative to our imaginary baseline, right? Like that's what you need to pass go to get your magical building permit, to get your lead sticker for the wall. So it could, but you're often hard pressed to find the willingness and the motivation to do it if there isn't a clear, project requirement for that happening.
And, a related question, I guess, in terms of kind of addressing the performance gap between models and actual is from Tomas. Is it a practice that you assess end use energy consumption after building construction to calibrate your consumption predictions for future projects?
Depends. Lots of projects where we're doing it, we have for net zero projects, we'll have a measurement and verification scope. So our energy model will continue. If you look at ASHRAE standard 209, there are several model cycles that happen during construction, where you update your energy model to match the as built. Even before a building is operated, I've never worked on a building project where it was built exactly the way it was designed, right? There's always a series of RFIs, changes, things that happen between the end of design and the end of construction. So first, the model needs to get updated to match the as-built condition. And then again, during operation to match the as operating condition. So yeah, when we work on, higher performing projects that have measurement and verification scope, we definitely do that.
And there's another question about tools and like tools for sensitivity analysis. And, can you provide a user-friendly tool for sensitivity analysis? I know there's probably different ways to answer that.
Yeah, I'll say it this way. I mean, you can use anything, really. It's just a matter of running it parametrically, right? So to run the same model like 10 times with like one thing varied a bunch of different times, that's the easiest way of doing it. I can tell you that OpenStudio has like a parametric module built right into it. So you could like build a model and say, what would happen if my tenants, heat this to 68, 69, 70, all the way up to 80 degrees, and it'll just run it automatically and give you all the results. So that's probably the lowest bar of entry to running sensitivity analysis.
And good. Yeah. So maybe one last question and then we'll wrap it up. So this was one that David asked earlier on in the presentation about, when you're talking about the process of predictive modeling and the idea of addressing model uncertainty. So he was asking for an example of addressing uncertainty in new construction, noting that, you can vary a parameter like roof insulation to see its impact on the model, but that approach assumes other parameters are correct or, that there aren't parameters that have, an indirect impact on that one.
It depends. Sorry to give you a hedging kind of answer, but that's how it is with uncertainty. But I can give a couple of examples, right? So for example, the Illinois Clean Energy Community Fund is an organization in Illinois that provides funding for public sector buildings looking for money to close the gap and hit net zero on new projects. And there, you have to go through a pretty detailed energy modeling process, and whatever the outcome of your energy modeling process, the ICECF makes you purchase that amount of PV plus 15%, right? So like that's how they handle the uncertainty. It's just by saying whatever it is, we're tagging on an extra 15% to you. But that's not ideal, obviously. So I would prefer to quantify it, right? And if I say that, based on this, my site energy consumption is X, I need, 100 kilowatts of PV. But, based on my sensitivity analysis, I'm showing that like this could vary by, up to 12%. Then I kind of know that, for me to really hit that net zero performance, I might want to consider buying at least 112, kilowatts of PV. So that's an example of how you can quantify your uncertainty and translate it to a real world, purchasing decision.
Great. Well, I really want to thank you, Ajit, for taking the time to share your experience with the ABIPSA USA community.
Absolutely.
I'll note that I did put a couple of links in the chat to more information about these 3 upcoming events in case you want to check those out. And otherwise, that's it for today's webinar, and hope to see you at a future event.
Thank you guys for the opportunity, and thank you for attending. Bye-bye.